As we've learned in the past modules, cloud providers offer us a bunch of different services. By now, we've learned a lot about different hosting models. If you're working for a small company, you might get by with prepackaged applications, offered in the software as a service model. But as the organization grows, so too do the IT needs. Eventually, your company might grow so large, you need to start developing your own applications based on the platforms and infrastructure models from cloud providers. Why might you develop your own application? Well, developing your own apps gives your IT team more control and flexibility over what the applications do. But it also brings a new set of challenges. You'll need to figure out how the different pieces fit together, make sure that the services run reliably, and troubleshoot problems when they come up. Almost all IT systems need to store some data. Sometimes it's a lot of data. Sometimes it's only bits and pieces of information. Cloud providers give us a lot of storage options. Picking the right solution for data storage will depend on what kind of service you're building. You'll need to consider a bunch of factors, like how much data you want to store, what kind of data that is, what geographical locations you'll be using it in, whether you're mostly writing or reading the data, how often the data changes, or what your budget is. This might sound like a lot of things to consider, but don't worry, it's not that bad. We'll check out some of the most common solutions offered by cloud providers to give you a better idea of when to choose what. When choosing a storage solution in the cloud, you might opt to go with traditional storage technologies like block storage. Or you can choose newer technologies like object or blob storage. Let's check out what each of these mean. As we saw in an earlier video, when we create a VM running in the cloud, it has a local disk attached to it. These local disks are an example of block storage. This type of storage closely resembles the physical storage that you have on physical machines using physical hard drives. Block storage in the cloud acts almost exactly like a hard drive. The operating system of the virtual machine will create and manage a file system on top of the block storage, just as if it were a physical drive. There's a pretty cool difference though. These are virtual disks, so we can easily move the data around. For example, we can migrate the information on the disk to a different location, attach the same disk image to other machines, or create snapshots of the current state. All of this without having to ship a physical device from place to place. Our block storage can be either persistent or ephemeral. Persistent storage is used for instances that are long-lived and need to keep data across reboots and upgrades. On the flip side, ephemeral storage is used for instances that are only temporary and only need to keep local data while they're running. Ephemeral storage is great for temporary files that your service needs to create while it's running, but you don't need to keep. This type of storage is especially common when using containers, but it can also be useful when dealing with virtual machines that only need to store data while they're running. In typical cloud setups, each VM has one or more disks attached to the machine. The data on these disks is managed by the OS and can't be easily shared with other VMs. If you're looking to share data across instances, you might want to look into some shared file system solutions that cloud providers offer using the platform as a service model. When using these solutions, the data can be accessed through network file system protocols like NFS or CIFS. This lets you connect many different instances or containers to the same file system with no programming required. Block storage and shared file systems work fine when you're managing servers that need to access files. But if you're trying to deploy a cloud app that needs to store application data, you'll probably need to look into other solutions like object storage, which is also known as blob storage. Object storage lets you place and retrieve objects in a storage bucket. These objects are just generic files like photos or cat videos, encoded and stored on disk as binary data. These files are commonly called blobs, which comes from binary large object. And, as we called out, these blobs are stored in locations known as buckets. Everything that you put into a storage bucket has a unique name. There's no file system. You place an object into storage with a name, and if you want that object back, you simply ask for it by name. To interact with an object store, you need to use an API or special utilities that can interact with the specific object store that you're using. On top of this, We've called out in earlier videos that most cloud providers offer databases as a service. These come in two basic flavors, SQL and NoSQL. SQL databases, also known as relational, use the traditional database format and query language. Data is stored in tables with columns and rows that can be indexed, and we retrieve the data by writing SQL queries. A lot of existing applications already use this model, so it's typically chosen when migrating an existing application to the cloud. NoSQL databases offer a lot of advantages related to scale. They're designed to be distributed across tons of machines and are super fast when retrieving results. But instead of a unified query language, we need to use a specific API provided by the database. This means that we might need to rewrite the portion of the application that accesses the DB. When deciding how to store your data, you'll also have to choose a storage class. Cloud providers typically offer different classes of storage at different prices. Variables like performance, availability, or how often the data is accessed will affect the monthly price. The performance of a storage solution is influenced by a number of factors, including throughput, IOPS, and latency. Let's check out what these mean. Throughput is the amount of data that you can read and write in a given amount of time. The throughput for reading and writing can be pretty different. For example, you could have a throughput of 1 GB per second for reading and 100 megabytes per second for writing. IOPS, or input-output operations per second, measures how many reads or writes you can do in 1 second, no matter how much data you're accessing. Each read or write operation has some overhead, so there's a limit on how many you can do in a given second. And latency is the amount of time it takes to complete a read or write operation. This will take into account the impact of IOPS, throughput, and the particulars of the specific service. Read latency is sometimes reported as the time it takes a storage system to start delivering data after a read request has been made, also known as time to first byte. While write latency is typically measured as the amount of time it takes for a write operation to complete. When choosing the storage class to use, you might come across terms like hot and cold. Hot data is accessed frequently and stored in hot storage, while cold data is accessed infrequently and stored in cold storage. These two storage types have different performance characteristics. For example, hot storage backends are usually built using solid-state disks, which are generally faster than the traditional spinning hard disks. So how do you choose between one and the other? Say you want to keep all data your service produces for 5 years, but you don't expect to regularly access data older than 1 year. You might choose to keep the last 1 year of data in hot storage so you have fast access to it. And after a year, you can move your data to cold storage where you can still get to it, but it will be slower and possibly cost more to access. There's a lot more to say about storage in the cloud. It's really quite a hot topic, but we won't go into more detail here. We'll provide links to more info in the next reading in case you want to learn more. Up next, we're going to look at a different cloud scale characteristic that we've already touched on, using multiple machines for the same service. In earlier videos, we saw a bunch of different reasons why we might want more than one machine or container running our service. For example, we might want to horizontally scale our service to handle more work, distribute instances geographically to get closer to our users, or have backup instances to keep the service running if one or more of the instances fail. No matter the reason, we use orchestration tools and techniques to make sure that the instances are repeatable. And once we've set up replicated machines, we'll want to distribute the requests across instances. We called out earlier that this is where load balancing comes into play. Let's take a closer look at the different load balancing methods that we can use. A pretty common load balancing technique is round-robin DNS. Round-robin is a really common method for distributing tasks. Imagine you're giving out treats at a party. First, you make sure that each of your friends gets 1 cookie. Then you give everyone a second serving, and so on until all of the treats are gone or your guests say, "Thank you, they're full." That's the round-robin approach to eating all the cookies. Now, if we want to translate a URL like myservice.example.com into an IP address, we use the DNS protocol, or domain name system. In the simplest configuration, the URL always gets translated into exactly the same IP address. But When we configure our DNS to use round robin, it'll give each client asking for the translation a group of IP addresses in a different order. The clients will then pick one of the addresses to try to reach the service. If an attempt fails, the client will jump to another address on the list. This load balancing method is super easy to set up. You just need to make sure that the IPs of all machines in the pool are configured in your DNS server. But it has some limitations. First, you can't control which addresses get picked by the clients. Even if a server is overloaded, you can't stop the clients from reaching out to it. On top of that, DNS records are cached by the clients and other servers. So if you need to change the list of addresses for the instances, you'll have to wait until all of the DNS records that were cached by the clients expire. There's got to be a better way, right? Well, there sure is. To have more control over how the load's distributed and to make faster changes, we can set up a server as a dedicated load balancer. This is a machine that acts as a proxy between the clients and the servers. It receives the requests and, based on the rules that we provide, it directs them to the selected backend server. Load balances can be super simple or super complex, depending on the service needs. Say your service needs to keep track of the actions that a user has taken up till now. In this case, you'll want your load balancer to use sticky sessions. Using sticky sessions means all requests from the same client always go to the same backend server. This can be really useful for services that need it, but can also cause headaches when migrating or maintaining your service, so you need to use it only if you really need it. Otherwise, you'll end up in a really sticky situation. Another cool feature of load balancers is that you can configure them to check the health of the backend servers. Typically, we do this by making a simple query to the servers and checking that the reply matches the expected reply. If a backend server is unhealthy, the load balancer will stop sending new requests to it to keep only healthy servers in the pool. As we've called out a few times already, a cool feature of cloud infrastructure is how easily we can add or remove machines from a pool of servers providing a service. If we have a load balancer controlling the load of the machines, adding a new machine to the pool is as easy as creating the instance and then letting the load balancer know that it can now route traffic to it. We can do this by manually creating and adding the instance, or when our service is under heavy load, we can just let the auto-scaling feature do it for us. Cool, right? Okay, so imagine that you've built out your service with load balancers and you're receiving requests from all over the world. How do you make sure that clients connect to the servers that are closest to them? You can use GeoDNS and GeoIP. These are DNS configurations that will direct your clients to the closest geographical load balancer. The mechanism used to route the traffic relies on how the DNS servers respond to requests. For example, for machines hosted in North America, a DNS server in North America might be configured to respond with the IPs in, you guessed it, North America. It can be tricky to set this up on your own, but most cloud providers offer it as part of their services, making it much easier to have a geographically distributed service. Let's take this one step further. There are some providers dedicated to bringing the contents of your services as close to the user as possible. These are the Content Delivery Networks, or CDNs. They make up a network of physical hosts that are geographically located as close to the end user as possible. This means that CDN servers are often in the same data center as the user's internet service provider. CDNs work by caching content super close to the user. When a user requests, say, a cute cat video, it's stored in the closest CDN server. That way, when a second user in the same region requests the same cat video, it's already cached in a server that's pretty close and it can be downloaded extra fast. Because no one should have to wait for their cat videos to load. You now know a lot of stuff about load balancing. Up next, we'll talk about another aspect of dealing with cloud services: how to deploy changes safely to our cloud service. You've come a long way. You now know how to get your service running in the cloud. Next, let's talk about how to keep it running. Most of the time when something stops working, it's because something changed. If we want our cloud service to be stable, we might be tempted to avoid changes altogether. But change is a fact of cloud life. If we want to fix bugs and improve features in our services, we have to make changes. but we can make changes in a controlled and safe way. This is called change management, and it's what lets us keep innovating while our services keep running. Step 1 in improving the safety of our changes. We have to make sure they're well tested. This means running unit tests and integration tests, and then running these tests whenever there's a change. In an earlier course, we briefly mentioned continuous integration, or CI, but here's a refresher. A continuous integration system will build and test our code every time there's a change. Ideally, the CI system runs even for changes that are being reviewed. That way, you can catch problems before they're merged into the main branch. You can use a common open source CI system like Jenkins, or if you use GitHub, you can use its Travis CI integration. Many cloud providers also offer continuous integration as a service. Once the change is committed, the CI system will build and test the resulting code. Now you can use continuous deployment, or CD, to automatically deploy the results of the build, or build artifacts. Continuous deployment lets you control the deployment with rules. For example, we usually configure our CD system to deploy new builds only when all of the tests have passed successfully. On top of that, we can configure our CD to push to different environments based on some rules. What do we mean by that? In an earlier video, we mentioned that when pushing Puppet changes, we should have a test environment separate from the production environment. Having them separate lets us validate that changes work correctly before they affect users. Here, environment means everything needed to run the service. It includes the machines and networks used for running the service, the deployed code, the configuration management, the application configurations, and the customer data. Production, usually shortened to prod, is the real environment, the ones users see and interact with. Because of this, we have to protect, love, and nurture prod. The test environment needs to be similar enough to prod that we can use them to check our changes work correctly. You could have your CD system configured to push new changes to the test environment. You can then check that the service is still working correctly there, and then manually tell your deployment system to push those same changes to production. If the service is complex and there are a bunch of different developers making changes to it, you might set up additional environments where the developers can test their changes in different stages before releasing them. For example, you might have your CD system push all new changes to a development or dev environment. Then, have a separate environment called pre-prod, which only gets specific changes after approval. And only after thorough testing, these changes get pushed to prod. See, you're trying to increase the efficiency of your service by 20%, but you don't know if the change you made might crash part of your system. You'll want to deploy it to one of those testing or development environments to make sure it works correctly before you ship it to prod. Remember, these environments need to be as similar to prod as possible. They should be built and deployed in the same way. And while we don't want them to be breaking all the time, it's normal for some changes to break dev or even pre-prod. We're just happy that we can catch them early so that they don't break prod. Sometimes, you might want to experiment with a new service feature. You've tested the code, you know it works, but you want to know if it's something that's going to work well for your users. When you have something that you want to test in production with real customers, you can experiment using A/B testing. In A/B testing, some requests are served using one set of code and configuration, A, and other requests are served using a different set of code and configuration, B. This is another place where a load balancer and instance groups can help us out. You can deploy one instance group in your A configuration and a second instance group in your B configuration. Then, by changing the configuration of the load balancer, you can direct different percentages of inbound requests to those two configurations. If your A configuration is today's production configuration, and your B configuration is something experimental, you might want to start by only directing 1% of your requests to B. Then, you can slowly ramp up the percentage as you check out whether the B configuration performs better than A, or not. Heads up, make sure you have basic monitoring so that it's easy to tell if A or B is performing better or worse. If it's hard to identify the backend responsible for serving A requests or B requests, then much of the value of A/B testing is lost to A/B debugging. So what happens if all the precautions we took aren't enough and we break something in production? Remember what we discussed in an earlier course about postmortems. We learn from failure and we build the new knowledge into our change management. Ask yourself, what did I have to do to catch the problem? Can I have one of my change management systems look for problems like that in the future? Can I add a test or a rule to my unit tests, my CI/CD system, or my service health checks to prevent this kind of failure in the future? So remember, if something breaks, give yourself a break. Sometimes in IT, these things happen, no matter how careful you are. And as you use and refine your change management systems and skills, you'll gain the confidence to make changes to your service more quickly and safely. We've spent a while talking about how to make your service run smoothly in the cloud. Now, let's take a moment to talk about some of the problems that you might come across. Personally, I find that when writing software to run on the cloud, it's important to keep in mind how my application will be deployed. The software I'm creating needs to be fault-tolerant and capable of handling unexpected events. Instances might be added or removed from the pool as needed. And if an individual machine crashes, my service needs to breeze along without introducing problems. And not every problem results in a crash. Sometimes we run into quotas or limits, meaning that you can only perform a certain number of operations within a certain time period. For example, when using blob storage, there might be a limit of 1,000 writes to the same blob in a given second. If your service performs a lot of these operations routinely, it might get blocked by these limits. In that case, you'll need to see if you can change the way you're doing the operations. For example, by grouping all of the calls into one batch. Switching to a different service is sometimes an option too. Some API calls used in cloud services can be expensive to perform. So most cloud providers will enforce rate limits on these calls to prevent one service from overloading the whole system. For example, there might be a rate limit of 1 call per second for an expensive API call. On top of that, there are also utilization limits, which cap the total amount of a certain resource that you can provision. These quotas are there to help you avoid unintentionally allocating more resources than you wanted. Imagine you've configured your service to use autoscaling, and it suddenly receives a huge spike in traffic. This could mean a lot of new instances getting deployed, which can cost a lot of money. Yikes. For some of these limits, you can ask for a quota increase from the cloud provider if you want additional capacity. And you can also set a smaller quota than the default to avoid overspending. This can be a great idea when you're running a service on a tight budget. If your service performs expensive operations routinely, you should make sure you understand the limitations of the solution that you choose. A lot of platform as a service and infrastructure as a service offerings have costs directly related to how much they're used. They also have usage quotas. If the service you've built suddenly becomes very popular, you can run out of quota or run out of budget. By imposing a quota on an auto-scaling system, the system will grow to meet user demand until it reaches the configured limit. The trick here is to have good monitoring and alerting around behavior like this. If your system runs out of quota, but there's an increased demand for puppy videos, the system may have problems, degraded performance, or worse yet, an outage. So you want to be notified as soon as it happens so that you can decide whether to increase your quota or not. Finally, let's talk about dependencies. When your service depends on a platform as a service offering like a hosted database or CI/CD system, you're handing the responsibility for maintenance and upgrades of that service off to your cloud provider. That's great. Fewer things to worry about and maintain. But it also means that you don't always get to choose what version of that software you're using. You might find yourself on either side of the upgrade cycle, either wanting to stay at a version that's working well for you or wanting the cloud provider to hurry up and upgrade to resolve a bug that's affecting your service. Your cloud provider has a strong incentive to keep its service software fairly up to date. Keeping software as a service solutions up to date ensures that customers aren't vulnerable to security flaws, that bugs are promptly fixed, and that new features get released early. At the same time, the cloud provider has to move carefully and test changes to keep disruption of the service to a minimum. They will communicate proactively about changes to the services that you use, and in some cases, cloud providers might give you access to early versions of these services. For example, you can set up a test environment for your service that uses the beta or pre-release version of a given software as a service solution, letting you test it before it impacts production. Hopefully, you're starting to get an idea of the trade-offs that you'll need to make to get the most from deploying your software to the cloud. As we called out in an earlier video, once we have our service running in the cloud, we want to make sure that our service keeps running. And not just that. We want to make sure it keeps behaving as expected, returning the right results quickly and reliably. The key to ensuring all of this is to set up good monitoring and alerting rules. In the next few videos, we'll do a rundown of monitoring and alerting concepts and techniques, followed by a practical demonstration. Let's dive in. To understand how our service is performing, we need to monitor it. Monitoring lets us look into the history and current status of a system. And how can we know what the status is? We'll check out a bunch of different metrics. These metrics tell us if the service is behaving as expected or not. While some metrics are generic, like how much memory an instance is using, other metrics are specific to the service we want to monitor. Say your company is running a website and you want to check if it's working correctly. When a web server responds to an HTTP request, it starts by sending a response code, followed by the content of the response. You might know, for example, that a 404 code means that the page wasn't found, or that a 500 response means that there was an internal server error. In general, response codes in the 500 range, like 501 or 503, tell us that something bad happened on the server while generating the response. While response codes in the 400 range means there was a client-side problem in the request. When monitoring your web service, you want to check both the count of response codes and their types to know if everything's okay. If you're running an e-commerce site, you'll care about how many purchases were made successfully and how many failed to complete. If you're running a mail server, you'll want to know how many emails were sent and how many got stuck, and so on. You'll need to think about the service you want to monitor and figure out the metrics you'll need. Now, once we've decided what metrics we care about, what do we do with them? We'll typically store them in the monitoring system. There's a bunch of different monitoring systems out there. Some systems, like AWS CloudWatch, Google Stackdriver, or Azure Metrics, are offered directly by the cloud providers. Other systems, like Prometheus, Datadog, or Nagios, can be used across vendors. There's two ways of getting our metrics into the monitoring system. Some systems use a pull model, which means that the monitoring infrastructure periodically queries our service to get the metrics. Other monitoring systems use a push model, which means that our service needs to periodically connect to the system to send the metrics. No matter how we get the metrics into the system, we can create dashboards based on the collected data. These dashboards show the progression of the metrics over time. We can look at the history of one specific metric to compare the current state to how it was last week or last month. Or we can look at the progression of two or more metrics together to check out how the change in one metric affects another. Imagine it's Monday morning and you notice that your service is receiving a lot less traffic than usual. You can look at the data from past weeks and see if you always get less traffic on Monday mornings, or if there's something broken causing your service to be unresponsive. Or, if you see that in the past couple days, the memory used by your instances has been going up, you can check if this growth follows a similar increase in another metric, like the amount of requests received, or the amount of data being transmitted. This can help you decide if there's been a memory leak that needs to be fixed, or if it's just an expected consequence of a growth in popularity. Pro tip: you only want to store the metrics that you care about, since storing all of these metrics in the system takes space, and storage space costs money. When we collect metrics from inside a system, like how much storage space the service is currently using, or how long it takes to process a request, this is called white box monitoring. White box monitoring checks the behavior of the system from the inside. We know the information we want to track, and we're in charge of making it possible to track. For example, if we want to track how many queries we're making to the database, we might need to add a variable to count this. On the flip side, black box monitoring checks the behavior of the system from the outside. This is typically done by making a request to the service and then checking that the actual response matches the expected response. We can use this to do a very simple check to know if the service is up and to verify if the service is responding from outside your network. Or we could use it to see how long it takes for a client in a different part of the world to get a response from the system. Okay, monitoring is really cool, But who wants to stare at dashboards all day trying to figure out if something's wrong? Fortunately, we don't have to. Instead, we can set up alerting rules to let us know if something's wrong. We expect a lot from our modern IT services. We expect them to be up and running 24/7. We want to be able to get our work done whenever and wherever. And for that, we need our services to respond, day or night, workday or holiday. But even if the services are running 24/7, system administrators can't constantly be in front of their systems. Instead, we set up our services so that they work unattended and deal with problems when they happen. Now, to do this, we need to detect those problems so that we can deal with them as quickly as possible. If you have no automated way of raising an alert, you might only find out about the issue when you get a call from a frustrated user telling you that your service is down. That's not ideal. It's much better to create automation that checks the health of your system and notifies you when things don't behave as expected. This can give you advance warning that something's wrong, sometimes even before users notice a problem at all. Okay, so how do we do that? The most basic approach is to run a job periodically that checks the health of a system and sends out an email if the system isn't healthy. On a Linux system, we could do this using cron, which is the tool to schedule periodic jobs. We'd pair this with a simple Python script that checks the service and sends any necessary emails. This is an extremely simplified version of an alerting system, but it shares the same principles as all alerting systems, no matter how complex and advanced. We want to periodically check the state of the service and raise alerts if there's a problem. When you use a monitoring system like the ones we described in our last video, the metrics you collect represent the state of your service. Instead of periodically running a script that connects to the service and checks if it's responding, you can configure the system to periodically evaluate the metrics and, based on some conditions, decide if an alert should be raised. Raising an alert signals that something is broken and a human needs to respond. For example, you could set up your system to raise alerts if the application is using more than 10 gigabytes of RAM, or if it's responding with too many 500 errors, or if the queue of requests waiting to get processed gets too long. Of course, not all alerts are equally urgent. We typically divide useful alerts into two groups, those that need immediate attention and those that need attention in the near future. If an alert doesn't need attention, then it shouldn't have been sent at all. It's just noise. If your web service is responding with errors to 50% of the requests, you should look at what's going on right away. Even if this means waking up in the middle of the night to address whatever is wrong, you'll definitely want to fix this kind of critical problem ASAP. On the other hand, if the issue is that the attached storage is 80% full, you need to figure out whether to increase the disk size or maybe clean up some of the stored data. But this isn't super urgent, so don't let it get in the way of a good night's sleep. Since these two types of alerts are different, we typically configure our systems to raise alerts in two different ways. Those that need immediate attention are called pages, which comes from a device called a pager. Before mobile phones became popular, pagers were the device of choice for receiving urgent messages. And they're still used in some places around the world. Nowadays, most people receive their pages in other forms like SMS, automated phone calls, emails, or through a mobile app, but we still call them pages. On the flip side, the non-urgent alerts are usually configured to create bugs or tickets for an IT specialist to take care of during their workday. They can also be configured to send email to specific mailing lists, or send a message to a chat channel that will be seen by the people maintaining the service. One thing to highlight is that all alerts should be actionable. If you get a bug or a page and there's nothing for you to do, then the alert isn't actionable and it should be changed, or it shouldn't be there at all. Otherwise, it's just noise. Say you're trying to check if your service's database backend is responsive. If you do this by creating a query that returns all rows in a large table, your request might sometimes time out and raise an alert. That would be a noisy alert, not really actionable. You'd need to tweak the query to make the check useful. Say you run a cron job that copies files from one location to another every 10 minutes. You want to check that this job runs successfully, so you configure your system to alert you if the job fails. After putting this in production, you realize there's a bunch of unimportant reasons that can cause this job to temporarily fail. Maybe the destination storage is too busy, and so sometimes the job times out. Maybe the origin was being rebooted right when the job started, so the job couldn't connect to it. No matter why, whenever you go to check out what caused the job to fail, you discover that the following run had succeeded, and there's nothing for you to do. You need to rethink the problem and tweak your alert. Since the task is running frequently, you don't care if it fails once or twice. You can change the system to only raise the alert if the job fails 3 times in a row. That way, when you get a bug, it means that it's failing consistently, and you'll actually need to take action to fix it. All of this configuring and tweaking can seem like a lot of work. You need to think about which metrics you care about, configure your monitoring system to store them, then configure your alerting system to raise alerts when things don't behave as expected. The flip side is that once you've set your systems to raise actionable alerts when needed, you can have peace of mind. If no alerts are firing, you know the service is working fine. This lets you concentrate on other tasks without having to worry. To set up good alerts, we need to figure out which situations should page, which ones should create bugs, and which ones we just don't care about. These decisions aren't always easy and might need some discussion with the rest of your team, but it can help make sure that you spend time only on things that actually matter. Up next, we'll talk about criteria that we can use to decide which situations should raise alerts and what to do about them. We all know that some IT systems are more critical than others. Let's be real. If you try to play a computer game that you haven't opened in a year and it doesn't work, you probably won't care as much as if you're trying to make a bank transfer and your bank's website is down. Sometimes a piece of infrastructure can be down and the overall system still works with degraded performance. For example, if the caching server that makes your web application go faster is down, the app can still function, even if it's running slower. No system is ever available 100% of the time. It's just not possible. But depending on how critical the service is, it can have different service level objectives, or SLOs. SLOs are pre-established performance goals for a specific service. Setting these objectives helps manage the expectations of the service users. And the targets also guide the work of those responsible for keeping the service running. SLOs need to be measurable, which means that there should be metrics that track how the service is performing and let you check if it's meeting the objectives or not. Many SLOs are expressed as how much time a service will behave as expected. For example, a service might promise to be available 99% of the time. Heads up. When dealing with metrics and availability, we need to do a little math to understand what those numbers mean in practice. But don't worry, it's all pretty straightforward. If our service has an SLO of 99% availability, it means it can be down up to 1% of the time. If we measure this over a year, the service can be down for a total of 3.65 days during the year and still have 99% availability. Availability targets like this one are commonly named by their number of nines. Our 99% example would be a 2.9 service. 99.9% availability is a 3.9 service. 99.999% availability is a 5.9 service. 5.9 services promise a total downtime of up to 5 minutes in a year. 5.9s is super high availability, reserved only for the most critical systems. A 3.9 service, aiming for a maximum of 8 hours of downtime per year, is fine for a lot of IT systems. Now, you might be wondering, why not just make everything a 5.9 service? It's a good question. The answer is because it's really expensive and usually not necessary. If your service isn't super critical and it's okay for it to be down briefly once in a while, having 2 or 3 nines of availability might be enough. You can keep the service running with a small team. 5.9 services usually require a much larger team of engineers to maintain it. Any service can have a bunch of different service level objectives like these that tell its users what to expect from it. Some services, like those that we pay for, also have more strict promises in the form of service level agreements, or SLAs. A service level agreement is a commitment between a provider and a client. Breaking these promises might have serious consequences. Service level objectives, though, are more like a soft target. It's what the maintaining team aims for, but the target might be missed in some situations. As we called out, having explicit SLOs or SLAs is useful for both the users of that service and the team that keeps the service running. If you're using a cloud service, you can decide how much you're going to entrust your infrastructure to it, based on the SLAs that the provider publishes. If, on the other hand, you're part of the team that maintains the service, you can use the SLOs and SLAs of your service to decide which alerts to create and how urgent they should be. Say you have a service with an SLO that says that at least 90% of the requests should return within 5 seconds. To know if your service is behaving correctly, you need to measure how many of the total requests are returning within those 5 seconds. And you want that number to always be above 90%. So, you might set up a non-paging alert to notify you if less than 95% return within 5 seconds, and a paging alert if less than 90% return promptly. If you're in charge of a website, you'll typically measure the rate of responses with 500 return codes to check if your service is behaving correctly. If your SLO is 99% of successful requests, you can set up a non-paging alert if the rate of errors is above 0.5% and a paging alert if it reaches 1%. In an earlier video, we called out that services usually break because something changed. That's also often the case when looking at what makes services go out of SLO. If your service was working fine and meeting all of its SLOs and then started misbehaving, it's likely this was caused by a recent change. That's why some teams use the concepts of error budgets to handle their services. Say you're running a service that has 3 nines of availability. This means the service can be down 43 minutes per month. This is your error budget. You can tolerate up to 43 minutes of downtime. So you keep track of the total time the service was down during the month. If it starts to get close to those 43 minutes, you might decide to stop pushing any new features and focus on resolving the problems that keep causing the downtime. Now, all this talk of nines, availability, and downtime can have your head spinning if you've never done this before, and that's totally normal. If it's your first time setting objectives for your service, start by setting achievable goals that you can measure. Track how the service behaves for a while, and see what causes the service to deviate from the targets. Once you have a better idea of the whole service's behavior, you can set more aggressive goals. Up next, we'll go back to our VMs running in the cloud and demonstrate how we can monitor them using the tools offered by the provider. So far, we've seen how to create virtual machines in the Google Cloud Console. We've kept these virtual machines running, and now we want to see how we can use the tools provided by the cloud vendor to monitor them and create alerts based on them. For this demonstration, we'll use the monitoring tool called Stackdriver, which is part of the overall offering. When you first activate this system, it takes a while until it starts collecting all the metrics from all the machines, so we've activated it in advance. When we first open the monitoring console, we see an overview of the system. At the moment, this is looking pretty empty, but we could configure this dashboard to show the charts that we consider the most useful. Let's go into the Instances dashboard. We see here the list of our instances, and we can click on each of them to see the monitoring information that Stackdriver has collected about them. The monitoring system gives us a very simple overview of each of the instances, with 3 basic metrics: CPU usage, disk I/O, and network traffic. Depending on what service we want to run on a VM, we can customize these dashboards to show different metrics. And if the metrics that come baked in aren't enough, you can create your own metrics and also add them here. Now, we want to check out how to set up an alert to notify us if something isn't behaving correctly. To do this, we'll create a new alerting policy. To set up a new alert, we have to configure the condition that triggers the alert. After we've done that, we can also configure how we want to be notified of the issue and add any documentation that we want the notification to include. Let's start by configuring the condition. As we called out, alerting conditions are related to specific metrics. We want to be notified when the metric indicates that there's a problem with an instance. For this example, we're going to configure an alert that triggers if an instance's CPU utilization is more than 90%. We'll start by selecting that we want to monitor GCE VM instances, which are the instances that we currently have running, and then select the CPU utilization metric. After selecting the metric, we see the graph of the collected values for all the current running instances. We can optionally add extra filters and groups for the data for this condition. For example, we could choose to only look at some of the instances, selecting by their zone, region, or name. This can be useful if you want to have separate alerts for instances used for production and those used for testing or development. On top of that, we can also choose an aggregator for the data. These aggregators are useful when the metrics that you're collecting are about the overall system and not just one instance. For example, if you're checking the number of error responses that your system generated, you want to sum all the errors across instances. Depending on how we filter, group, and aggregate the data, we'll end up with a bunch of different time series. We'll use these values to decide if we should trigger the alert or not. The next step is selecting how many of the different time series need to violate the condition for the alert to trigger. We can trigger the alert when one, some, or all of the different time series violate the condition. For this example, we'll configure our alert to trigger if any instance is using more than 90% of the CPU. So let's select any time series violates. And now we'll say that we want our alert to trigger if the value is above 90% for 1 minute. All right, we've set the condition. Now we can select how we want to get the notification when the alert triggers. Currently, the only type of notification that we can use is email. To use the other channel types available, we need to configure them in our profile. For this example, email will do. Using emails can be just fine when you're getting started with alerting, but eventually you'll want to configure additional methods. All right, we've configured our alert to send emails. Now we can add extra documentation to our alert. This documentation is intended to help the person that's responding to the alert understand what they need to do to fix the problem. Including good documentation here can be super important when you've got a bunch of different people working together in a team and not everyone knows everything. Alerts that include good documentation are much easier to tend to and help get the service back to a healthy state faster. For our example, we'll add a message saying that whoever is taking care of this alert should check the instance with top. Finally, we'll need to give a name to our alerting policy. We'll call it CPU, and then save it. Woohoo! Now we've set up our alert. Now we can sit back and relax, knowing that if anything goes wrong, we'll be the first to know. For the final part of this demo, we want to show what happens when the alert triggers. To do that, we'll start a process in one of our instances that uses all of the available CPU by creating an infinite loop. So we'll go back to the main console, SSH into the VM called Linux-instance, and then create a while loop that never ends. Now our loop is running and using all of the available CPU. We can check this by running the top command that shows us the CPU usage. We see that there's a bash command that's using almost 100% of the available CPU. Our experiment is working. Now, remember that we said that we wanted the condition to be true for a minute before the alert triggers. It won't trigger just yet. It's common practice to use time windows of 1, 5, or even 10 minutes when dealing with the alerting. We don't want to get an alert for a small spike that lasted only a few seconds and then went away. We want to get alerted when there's an actual problem that requires our attention. The size of the time window we choose depends on the metric we're checking, the length of the expected spikes, and a bunch of other factors. It's pretty normal to have to tweak how long we want the condition to be true as we try our alert out. If you're getting notified too often about conditions that go away on their own without you having to do anything, you might choose to make the time window larger. On the flip side, if you're getting notified too late about conditions that needed attention, you might choose to make the time window smaller. All right, we've let enough time pass. Let's check out what's up with our alert. We see that there's an open incident, which is a way of grouping problems. The alert summary gives us a bunch of info about what's going on. We can click on the CPU link to get more information. This page shows us the metric that triggered the alert for the incident. It shows the threshold for triggering the alert and the current value of the metric. It also shows us the documentation that we entered and lets us create annotations. We can use these annotations to track the work that we do during an incident. Alright, let's stop the process that's using all of our instance's CPU. It's still running the top process from before. Let's exit with Q. Now, the infinite loop is currently running in the background of our console. We can make it run in the foreground by typing FG and then cancel it by pressing Ctrl-C. Okay, now we've stopped the process. Let's check with top that it's no longer using all of our CPU. Great, the bash process isn't taking all of the CPU time anymore. In another minute, the alert that we saw earlier will stop triggering. Nice. And with that, we've demonstrated how we can monitor a bunch of instances running in the cloud. We've created an alert based on metrics and verified that the alert triggers. Of course, there's a lot more that we can do with these tools. If you're used to troubleshooting problems on physical computers, it can take a bit of a mindset shift to get used to fixing problems with virtual machines running in the cloud. There's a bunch of things that you can't do, like you can't walk up to a server and check out what's wrong with it. But there's also other things that are a lot simpler when troubleshooting VMs in the cloud, like adding more memory or moving the machine to a different data center. Let's say that, after the latest upgrade, a bunch of your cloud VMs have stopped booting. Something went wrong, but you don't know exactly what. You can't connect to the instances or boot them in rescue mode. So what can you do? There's a bunch of options. If you're following the infrastructure as code practices that we've talked about, you could deploy new VMs with the previous version of the system. This would help us get back to a healthy state as quickly as possible. On top of this, you want to understand the problem and how to fix it. To do that, you can create a snapshot of the disk image for one of the failing VMs, and then mount that disk image on a healthy machine. That way, you can analyze the contents of the image and figure out what's causing the failures. Now, it's not always easy to know which piece of the system is causing a failure, especially if the system is complex, with many different services interacting with each other. If you're trying to figure out what's causing your complex service to respond with a ton of 500s, you need to look at different pieces individually until you find the culprit. Does the problem happen if you run the service in a test VM without any load balancers or caching servers in between? Does it happen if you run the service locally on your workstation? The more you can isolate the faulty behavior, the easier it is to fix it. You should remember that problems will happen. It makes sense to spend some time getting ready for them. Setting up a testing environment might take time and effort, so it's a good idea to do this in advance before any problem actually happens. That way you don't need to do it under pressure when your users are complaining that the system's down. Say you're using a database service that's only reachable from inside your cloud network. This means you can't interact with it directly from the outside, only from instances within your cloud infrastructure. If your service starts acting up, you might want to check the responses from the database directly, rather than going through any of the other backend servers. To do this, you'll need to have a debugging machine in the network, and you'll need to use tools to interact with the database directly. Again, setting the machine up and learning how to use the tools takes time, so get ahead of the game and do it in advance before any problems come up. You might remember from the troubleshooting and debugging course that understanding logs is super important for being able to solve problems in IT. When you run your service in the cloud, you need to learn where to find the logs that the provider keeps and what info is available in which logs. Some cloud providers offer centralized log solutions to collect all your logs in one place. You can have all your nodes send info, warning, and error messages to the log collection point. Then, when you're trying to debug a problem, you can easily see everything that was going on when the error occurred. Up next, we'll check out more strategies that you can use to get to the root cause of your cloudy problems. As we've called out a few times, when we host our services in the cloud, we need to give up part of the control over the infrastructure that we're using. This might be especially noticeable when we're trying to find the root cause of a problem in our service, and we don't know if the failure is caused by an error on our side or on the provider's side. So what can we do in that case? Problems on the provider's side tend to be isolated to geographical regions. If you're seeing weird problems and you have no idea what could be going on, you can try bringing up your service in a different region and checking if the failure happens there too. If it works fine there, it's likely that there's an issue with the cloud infrastructure, and you should bring it up with your provider. If it fails in the other regions too, it's likely that it's a problem with your system. Similarly, if you're seeing problems related to resource usage, you can try running the same system in a different machine type and checking how it behaves there. This could help out, for example, if your service takes too much time to process incoming requests. By changing your service to more powerful machines, you might improve the overall performance. Another option that we've mentioned a bunch is doing rollbacks for the pieces that have recently changed. Having all your infrastructure stored as code in a version control system will let you access the history of the changes to each component in the system. When setting up your service, you should make sure that you can deploy and roll back each individual piece. Imagine you get an alert saying that the web servers in your application are using a lot more memory than they used to. You don't know why, but you know that a new version was deployed a couple of days ago. By rolling back to the previous version, you can verify if that change was at fault or not. If the servers work fine after the rollback, you can investigate the specific changes and try to figure out why they're using so much more memory. If the servers are still using a lot of memory after the rollback, it means something else is up. In an earlier video, we touched briefly upon one popular option when running things on the cloud, called containers. Containers are packaged applications that are shipped together with their libraries and dependencies. Each application is executed in a separate container, completely independent of any other applications running on the same machine. Now, one of the neat characteristics of containerized applications is that you can deploy the same container to your local workstation, to a server running on-premise, or to cloud infrastructure provided by different vendors. This can be really helpful when trying to understand if the failure is in the code or the infrastructure. You simply deploy the container somewhere else and check if it behaves the same way. When using containers, the typical architecture is to have a lot of small containers that take care of different parts of the service. This means that the overall system can get really complex, and when something breaks, it can be hard to identify where the problem is coming from. The key to solving problems in the container world is to make sure you have good logs coming in from all of the parts of the system, and that you can bring up test instances of each of the applications to try things out when necessary. Up next, we'll talk about some of the tools that we can use in the cloud to recover from outages. When dealing with a complex system, there's a lot of ways it can fail. If we want our service to be reliable, we need to make sure that we can get it up and running as quickly as possible when bad things happen. We'll need to have good backups and a well-documented recovery plan. Backups here doesn't mean just copies of your data. It also means backups for the different pieces of your infrastructure, including the instances that are running the service and the network that's used to connect to the service. Backups of the data your service handles are extremely important. If you operate a service that stores any kind of data, it's critical that you implement automatic backups and that you periodically check that those backups are working correctly by performing restores. This helps make sure that you're backing up the right data and that you have well-documented processes for recovering it when things fail. What about the rest of the infrastructure? If you store all your infrastructure as code, you already have a backup of what your infrastructure should look like. But if your service goes down for some reason, deploying all that infrastructure from scratch might take a while. That's why many teams keep backup or secondary instances of their services already up and running. That way, if there's a problem with the primary instance, they can simply point the load balancer or the DNS entries to the secondary instance with minimal disruption to the service. Alternatively, it's common practice to have enough servers running at any time so that if one of them goes down, the others can still handle the traffic. Or, on a larger scale, have the service running on different data centers around the world so that if one of the data centers has a problem, the service can still be provided by the instances running in the other data centers. If you're running a service on-premise, you might want to have 2 different connections to the internet. This way, if the connection offered by one of your ISPs goes down, you can still connect to the internet through the other one. When you're running on cloud, you can mostly rely on your cloud provider having enough network redundancy. But if you really care about your service staying up no matter what, you might want to run your service on 2 different cloud vendors so that if one of the providers has a large outage, you can still rely on the other. Now, imagine you're running your service in one data center. Unfortunately, that data center has just suffered a natural disaster, and all of your instances are down. What do you do? First step, deep breath, don't panic. You need to recover your service from scratch, deploying it in a different data center and getting all your data from backups. As long as the backups are available in other data centers and your infrastructure is fully stored in a version control system, this should be possible. But figuring out how to successfully bring up the whole system from scratch can take a while. So you don't want to have to scramble to do it when disaster hits. Instead, you should have a documented procedure that explains all of the steps that you need to take. And since systems evolve over time, you need to make sure that this documentation stays up to date. One way to do that is to once in a while pretend that you need to recover your service, follow the documented steps, and check if anything is missing or outdated. Systems will fail. 100% availability is simply not an achievable target. But being prepared for a failure will let you recover your service quickly and keep your users happy. Up next, we've gathered some resources to give you more info on how to debug problems on the cloud and to be ready for when things fail.
Congratulations on finishing this lesson in the Google IT Automation with Python certificate. Access the full experience, including job search help, and get the official certificate by clicking the icon or the link in the description. Watch the next lesson in the course by clicking here, and subscribe to our channel for more lessons from upcoming Google Career Certificates.